Cool.
Oh wait, are you capturing anything on OBS, Josh?
Yeah, I'm just capturing like video and audio.
Oh, it
Yeah.
is capturing the whole thing. Okay.
Yep.
Okay.
All right. So we're going to start with an introduction to C strings because these are like the most buggy thing in C. So C string, if you're coming from like Java or Python or something like that, strings are like a class, right? You have like, I should have come with examples prepared, but you can do like string.length or string.len or whatever it is in Python. And that works fine. And the string knows its own length. In C, that's not a thing. The way strings are represented is you have the contents of this string, like a bunch of characters in a row, and then what's called a null terminator. And the null terminator is where you know how you know that the string ends, because there's no length associated with it. So the way you know how big the string is you read until you get to this null terminator, it's called. It's just like a 0. And then you're like, okay, that's the end of the string. And this makes things in C really annoying to do. So for example, this is string copy in C. So this like copies from the source string right here into the destination string. And this is just like a simple implementation what the standard library could look like. And notice here how you always have to make sure it has this null terminator, because if you don't, then well, think about it. Like if say you have like Sterling, or like find the length of a string. So what it does is it reads the first character, not a 0, second character, not a 0, third character, so on. If there's no 0, it just keeps going, like on into memory. So here's an example of that, sterling.c. All right. So this is like super simple. You start with a length of 0. While this pointer isn't equal to 0, increment the length. If we got to 0, then we're done, so return the length. And this is like the right way you'd use it. You have a null terminated string. You say, what's the length? And it prints out the length. So let me open that in the terminal. All right, Sterling. And it says, OK, it has length 13. And then say we want to find the length of like an arbitrary string, right? The user prints in some string, like say hello. Oh, well, I have this assert here. All right, so I have another file, one sec. That's called y, and it just has like a bunch of y's in a row. All right, so we're going to run this program, Sterling from y. And you see here already bad things have happened. So what happened here is we didn't make sure that the string was null terminated. We read from standard in into our buffer 1,000 characters. And then, so I actually had to fiddle with this a bit. The compiler was trying to be too smart, and one passed the end of the buffer even though we didn't write to it with 0. Anyway, but if you had that string that isn't terminated, then it just keeps going. It tries to print the string, and there's like this random garbage at the end, and then like the libc implementation says, oh, something's up, and then the whole thing just crashes. And this is really easy to do in C. All that it takes is one string that doesn't have that null terminator at the end. So what can you do? Well, really there's not much. The answer is make sure all your strings are null terminated, but you don't have a way to tell whether they're null terminated or not. Like the way you do that was with Sterling right here, and we just saw how that goes with this crash. So the way you stop crashes in C is don't write the crashes in the first place, which is not the best approach for software security. So, well, okay, maybe we could just ensure that all our strings are null terminated. That doesn't sound like the worst thing in the world. Let's see some more examples, like stir copy. This takes, okay, here's our source string, here's our destination string. Now, because this is C, we don't have infinite memory. We can't just say write this to somewhere. We have to say where that somewhere is. So the somewhere in this case is car destination, and I said it has length 10, and this is like allocated on the stack. So
are you able to zoom in, Josh?
I am able to zoom in. Can everyone see that?
Yeah, that's better, thanks.
Yeah, awesome. All right, so I've allocated this array of characters that has length 10, and it's on the stack. Does everyone know what I mean by allocated on the stack?
Can you go over it?
Yeah, this one here. Yeah, so allocated on the stack is like when you enter a function. Here, I actually had this open a little earlier. So when you call a function, there's a picture too. Here we go. You have like your executable code, which is like the ones and zeros the compiler generates. You have static variables, which we'll go into in a second, and then you have the stack. And so like for every call to a function, you get a new what's called a stack frame, and it's like an area of memory where you get to put your variables. So this like dest10 would be somewhere in here. And when you return from a function, this memory on the stack goes away. The compiler's like, oh, the function's done. No need to keep that memory around anymore. Does that make sense-ish? Okay, I'm going to go with that. So we've allocated this memory on the stack. The compiler kind of does it for us. It says, okay, you need 10 bytes. And we say copy hello world into destination. Well, there's a problem here, because hello world is more than 10 characters. So what happens? Well, what happens is it'll go through all those characters. It'll write to every one of them from the source. So it's going to write, I think this is 16 characters. And let's see what that looks like. If I can find a terminal. So this is, did I call this stir copy? Yeah, it's a stir copy. Right, so it seems to have worked. Ignore the second line, that's from something else. It seems to have worked. It printed hello world. Actually, let me print this out afterwards so you can see it. So this says, put this whole string to standard out. Right, and it can already see, the compiler is giving us a warning. Hey, you're copying 14 bytes into a string that's 10 bytes long, but let's try it anyway. So it seems to have worked. And this is what's called undefined behavior. It could work, it could not work, it could blow up your computer, it could just do nothing. You don't know. So generally you try and avoid undefined behavior. In this case, the compiler didn't do anything bad. Well, all right, that doesn't seem like the worst thing. What else can go wrong? So say we know like this is a problem that can occur. We're like, all right, well, we know how big destination is. Can we just say copy at most 10 bytes into it, right? So we do, there's a function for that in the C standard library. It's called stir and copy. And it says copy this string into the destination, but only do at most 10 bytes, because it can only store at most 10 bytes, right? So this doesn't immediately give us undefined behavior, but what it does is it puts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those bytes in, and it doesn't put the null terminator. So we have the same problem from before where it's not null terminated, but now we don't know, right? So the way we could have checked that is we could say, if destination 9 is not the null terminator, oh, we should actually have done that. But in the meantime, what we get here is the stack smashing detected again. It's going beyond the end of the string, and it's trying to print out everything in memory that follows, which is clearly not what we want. And we're like, okay, well, let's do the thing we did from before. We know it's 10, set the one at 10 to null, even if it's not null already. Except we don't need 10, we need 9. Oops, there's another bug, right? So the issue here is you can't avoid these bugs, but it's annoying, and the compiler doesn't warn you, is kind of the gist of things. It's the way you write code correctly is write it correctly the first time. I'm sad Charles isn't here. Anyway. So the easier way to do this is you say, okay, well, we know that stir and copy is not going to copy in a null terminator if it's not big enough, so just tell it it's smaller than it is. And like initialize it to 0 or something. Like dest, the same thing we had before, dest 9 equals null terminator. And this will work even if stir and copy didn't put it in for us. And if anyone's interested, I can send this code after. This is what stir and copy looks like in the standard library. Questions so far? I know I have the tendency to go pretty fast.
So it seems really simple to avoid this undefined behavior with strings. But how complicated can it get with, a bigger project?
Yeah, so that's the thing, is you you have to do it right every single time. If you're looking at this, you're like, okay, well, I did it right this one time and it's good. But like, if someone else in a completely unrelated part of the project forgot to do this and they put in a 10 instead of a 9, all of a sudden you've got a string that's not a string, and the second you use it, it's going to crash somewhere else, like later in the program, long after the bug. So that's kind of the poisonous thing about this, is it's non-local. The bugs show up later.
Josh, are there any compiler flags that you can send to warn for null termination?
Not really, because most of it is done at runtime. Now you can do what's called instrumenting your binary, and instrumenting is like have a different standard library that checks whether you're doing things right. And the tool for this is called valgrind, and it says, okay, every time I access a bit of memory, check if that access is valid or not. And that will usually catch this sort of bug, but it makes the program much slower. So people only do it in test suites, and not everyone does it in their test suite. And it only catches things at runtime. So like, say something only happens occasionally, valgrind won't catch it.
Okay, that makes sense.
Yeah. More questions before I go on? Cool. All right. So the last thing I wanted to do in C before we go on is stir cat. So this is just like concatenate two strings. And this is like what the standard library would look like. I'm going to skip it because it's not super important. So first of all, when you like, so in Java, this would be like A, B, C plus E, F, G. Like literally you just write plus and Java does it for you. That doesn't work in C. This is like a compile error. It says the types are wrong. So what you do instead is there's a function called stircat, and it says, okay, take the destination, take the source, and just like concat them together. So the idea here is that we're going to end up with A, B, C, G, G, E, F, G. Ignore this, it's not super important for the example. This does not work. If you do this, it will crash your program. And the reason for that is, remember I was talking about static memory before? You have the code, you have the stack, and you have these magical static variables. What these static variables are is like a section of the binary, like on the disk, where it's reserved space for these static strings. A, B, C, hello, all these things are living in static memory in the binary. And these are marked as read-only memory. So the second you try and write to them, you get like a segmentation or fault or something. Like the OS says you can't do that. It's not allowed. Stircat. Yeah, and you see here before it does anything else, just immediately crashes. So you're like, okay, well, let's try doing this differently. Let's do it right. So this is bug 2. So we're allocating some stack memory. So it's 10 bytes, so it's more than big enough for this string, and we're concatenate these two together. So let's run that and see what it does. Stircat, sorry. Right, and that crashes too. What's going on here? Destination here has the same bug from, wrong terminal, sorry. Destination here is the same bug from before. It's not null terminated. If you concatenate two strings, they have to both be strings, and this is just some random bytes. So you see here the bug from before is kind of popping up again. So what could you do instead? You'd have to initially, like, explicitly allocate it. Or, sorry, explicitly initialize it. Or something like that. If I could type, there we go. And this says make the first character 0, and we don't care what the other characters are. And then if I did everything right, oh, here, let's put this so we can see what's going on. Yeah, so we see here it gets a little bit farther before it crashes this time, because we made sure that this is a valid string in C parlance. It ends with the null terminator. Does that make sense? Sort of. Cool. And then it's the same issues from before here too. If you don't have enough memory allocated, allocated for the string, then it goes past the end of the buffer, and you have issues. So you're like, okay, you stir and cat again, and then you have off by 1 errors. And then this is like the right way to do it: is you stir and cat 1 less than the length of the buffer world. which is kind of annoying for something that is literally like ABC plus EFG in Java. But it works. It will work. You just have to do it completely right every single time in all parts of your program. Right. So what alternatives do we have? Things are looking pretty like annoying and hard to work with if we have to do it right every single time, and it's kind of annoying to do it right. Well, this is why C++ was invented, because people really hated that sort of thing. Wrong one. One of these. Did I not put it here? Oh yeah, stir.c. Here it is. Okay. So in here it looks basically like Java. You say string s, hello, string plus world. And it takes care of all the annoying things that you had to do in C. It takes care of making sure the string is big enough. It takes care of making sure that it's null terminated. And it knows how big it is. So you can do like string.length, and that's like not a problem. It's not... String.length in C++ will never crash your program. So this is good. This is like a major leg up over C. But you can still write C in C++. You can still say like strcat hello world, and like it'll compile and then crash later. So you have to be less disciplined, but you still have to make sure you're using the C++ things instead of the C things. Which is like where people get into holy wars, and they're like, oh, you're writing old C++, and old C++ isn't as good as new C++, blah, 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 blah. So this is one of the things that C++ makes really nice, is dealing with strings. Yeah. Cool. C++ has other issues, though. And one of those issues... Oh, actually, let me go back to C for a second. Another problem that you see in C is, remember how I said that things are stack allocated, and things that are stack allocated go out of scope at the end of the function? This is like a little get line that I wrote. So the idea is you write, while true, get line. If it says to quit, then quit. Otherwise, print the line. So if you try and do this from the heap, if you try and, get a line, allocate some memory on the stack, return the line, this is immediately undefined behavior right here. And the reason for that is because you're returning a pointer to memory that's gone away. Like you returned from this function, this buffer here has been deallocated, and you can't use it anymore. The second you touch this buffer, the whole thing blows up. So how do you return a string? How do you return a string in C? Well, what you have to do is allocate it on the heap. So there is one more part of this picture I haven't looked at. We have the code, that's your program. We have the static variables that live in the binary. We have the stack, which has like a different, what's called a stack frame for each function. Right, so this is one function's variable, so on. And then we have the heap. And the heap is like long-lived memory. So you say, okay, allocate some memory on the heap, such amount, and then it just sticks around for a while until you call a function that's called free. So free says, okay, we had this memory on the heap, and we're done using it, so just deallocate it. We don't need it anymore. So that's what this one does. This function is exactly the same as getLineStack, except for this line here, which says give me memory on the heap instead of on the stack. And then this is some annoying string handling in C, which don't do string handling in C. It's really awful. I had like 4 bugs before I finished this. And then you have to make sure it's null terminated, and then you return the line. And this works. So if you use this in like the naive way, okay, make a pointer, read the line. If it's equal to this, break. Otherwise, print out the line. So let's see what that looks like. This is malloc. Oh, I didn't give it a name. So it prints all the lines that I'm typing in. Sorry about the dog. It prints all the lines I'm typing in. I say quit, and it quits. Okay, that doesn't seem so bad. The problem is, like, say you have a web server or something, and the web server is up for weeks on end, and it serves thousands of requests every hour, and you have this little line of code here. there's nothing here that's a bug. It's what's missing that's a bug. What you need is a free line. If you don't have this line right here, whoops, sorry, then the memory that you allocated for line will never be deallocated. So you've like said, okay, give me this much of the heap, and then you just like keep saying, give me more of the heap, and then eventually you run out of heap. And at that point, normally you get like an out of memory, or your program crashes or something like that. It's not the worst thing in the world. It causes service outages instead of security flaws, but it's still not good. Questions on like dynamic and static memory. Dynamic memory is like memory allocated on a heap. Okay. So the other issue you have with dynamic memory is you can use these exactly until you call free, and the second you use it afterwards, it is undefined behavior. So if you have, actually I can just do the example. What was it? This is malloc free. Okay. GCC malloc free. Okay. I'm gonna do this is the one that's try 1 that never freed the memory. And I'm gonna say quit, and this is try 2. Oh, we have a problem here. What happened? So it says double free or corruption. What happened here is that we tried to use it after we freed it, which is a big no-no. You can't do that. So in C, the solution to this is do it right. There is no solution. There's no way to tell whether you freed a pointer or not. It's the same pointer before and after. So you can either do things like reference counting the pointer. You can say like, okay, struct address and like whether it's been freed. Yeah, something like that. But like, there's not a way built into the language. You have to remember to update freed after you free it. I mean, it's not pleasant to work with. And nobody does this in real code because it like adds like size to the struct here, like takes up more space in memory, and you have performance overheads, and nobody does it. People were just like, oh, we'll just do it right the first time, and sometimes they do, and sometimes they don't. So actually, let me come up. Literally, I don't even have a pre-existing example because I'm so sure this is going to come up. Literally, this is like a category of vulnerabilities on common weakness and enumeration. It's like a security site. I want an example. Oh well. Anyway, so this is like a common thing that pops up in C programs all the time. So how can we avoid this? There's not a great way to do it in C, but maybe C++ has a way to do this. And in fact, it does. It has something called RAII, which is short for Resource Acquisition is Initialization. And that is a fancy word for when we like declare a string, we initialize it at the same time. And when the string goes out of scope, we deinitialize it at the same time. We free the memory automatically. The compiler does it for us. And that's where you get like constructors and destructors and stuff. If you've taken a C++ course, the destructor is what's called when the string goes out of scope. And in the case of standard string, it's like calling, libc free or something like that. Yeah. So in this case, this is actually like not so bad in C++. It initializes it automatically. It allocates all the memory we have to automatically. It returns this string because it's heap allocated, so we can do that. We do a little check from before, we print it out, and then it's automatically freed here. We don't have to remember to add a free. So here's, I don't think I actually have the make rule for this. And I have to compile it. Yeah, this is the bad thing about C++ is the error messages are awful. Okay, and we can do the same thing from before. It's an echo server unless we say quit, and then it quits. So this isn't so bad. Questions on RAII and like what I'm doing in life and that sort of thing? Oh, Dustin had a question. What about changing it to null? If it's null, I deallocate. So that works if you have exactly one copy of the pointer. If you've like shared the pointer with another part of your program, then you can't modify it anymore. So it will still have the original pointer, and it actually doesn't know at all whether that pointer has been freed. There's no way for it to tell. So changing it to null works if you only use it in one part of your code. Other questions before I go on? What if I have a pointer to the pointer? Then you have performance issues because you have to do 2 memory deallocations, and you don't want to do that for every single pointer in your program because now it's twice as much. And what if your pointer to the pointer has to be allocated somewhere, right? Where is that? I don't know. It's possible, but I don't know anybody who does things like that. But I have heard people suggesting like you pass a pointer to free, and like free will set that to 0 for you automatically. But I don't think anything came of that. Oh, wrong program. Free is the standard library function that says deallocate this memory for me. All right. So far it sounded like C++ is amazing and it fixes all the C memory programs. And why are there still memory bugs if people are using C++? Well, the answer is that C++ doesn't fix all of those memory problems. So I'm going to watch a short video here if I can get Vim to not be awful. There we go. Oh, well, sorry. I've configured my computer too much, clearly. Right. Actually, let me just paste this into Discord, so I'm not trying to send video over chat. All right, and you can watch this later if you want. The gist of it is that the most common bug that Facebook has in their code, in all Facebook, is this function right here. This function is getDefault. It takes a map, like a hash map from a string to another string. It takes a key, and it takes a default value. And it says, if you find the key in the map, return the value you found. So that's this position dot second here, the value you found. Otherwise, if you didn't find it, return the default. And this code is hopelessly broken. And the reason it's hopelessly broken is this little ampersand here. This ampersand means return a reference, which normally is a good thing because it lets you avoid copies. But in this case, what are you returning a reference to? Well, either you're returning a reference to something in the map, that's this thing here, or you're returning a reference to the default. Well, what happens if you have, say, a function that takes in a map and it does some computation and it says get default from the map with like a temporary value, right? So this is we're like getting an IP address, and the default value is the IP address. And if there's already an IP set, then return that IP. Otherwise, return like localhost or something, right? Say this is like a heap allocated string that we've allocated, right? If you return a reference to this string and then deallocate it later, then the second you use it, it goes boom again. You've run into the same issue from before, but like with more indirection now. Because now you need like intermediate functions and stuff, but it's still going to go boom eventually. Let me write this code out. Hold on. String s equals localhost. Right.
Wait, Josh, why don't they just do pass by copy here?
Yeah, so that's the fix is you pass by copy, and that works. That absolutely makes this function like not do bad things, but then you make a copy every time, which the C++ people really hate because it hits your performance. So, yeah.
But it can't be that crazy bad of a performance hit, because that string's still going to be there for as long as, I mean, those primitives are still garbage collected, aren't they?
No, C++ isn't garbage collected unless you use, I think, like shared pointer. But all these strings here use RAII, the constructor-destructor thing I was talking about. So if you say make a copy of it, it will make a second copy. So it goes through the whole string. This one isn't very long. But like, say the one we had in the map was really long, it would make a copy of the whole thing before returning it.
I see. Okay.
Mm-hmm.
So it's a very specific, well, not that specific, but I guess it's a very general case for them that they use this a lot.
Yeah, well, you can imagine it's like a common thing, right? Like in Python, I think this is built into the standard library. And it's not in C++ for this exact reason, because you can't return a reference because that breaks things, and you can't return it by value because then people get annoyed at performance.
How would Python go about dealing this then? I mean,
Python makes
I
a
guess-
copy. Python has this version of it.
I see.
Or I think. Or it uses reference counters. I'm not sure how Python works internally. We'll do one of the two. We'll talk about reference counting in a second. And there's a second bug here. Has anyone noticed it yet? It's specifically in this function in helper. I'm gonna give it a minute.
Did you already say S could be dereferenced as it? I mean, it is a local variable, so it would get so if it's not by copy, it would get taken off the stack. I think in this case.
Yes, exactly. Yep. If you return a reference to S, then you're returning a reference to free memory. And actually, if you return a reference to something that was in the map is also a local variable, so that would be free memory as well. So you got to be careful with these things. C++ does not catch this error, by the way. Let me give you what G++ does on this file. Oh,
What is your
well, I take
compiler
it
say?
back. It says returning reference to temporary variable. So that is
Yeah,
helpful.
GCC has gotten really good over the years.
I'm,
Even through my years of college, it's gotten better.
You took off the ampersand, so it's doing the.
This one's correct now, but the get default is now correct because I removed the ampersand, but helper is still wrong.
No, what I'm saying, if you put the ampersand back into get default,
No, it will not catch
I
that.
think
either.
that's where you have the issue.
That also will not help. It actually gives fewer errors than before. That's kind of sad. So it's like a very ad hoc thing. This trying to catch an error that it does. It's not very smart about it.
It's like how my compiler is written.
Yeah, sort of. And this is like another example of it that I think is less clear than the original. But so the question is, how do we solve this now? This was kind of like a tricky bug to find, right? Like you had to think about it a little bit, especially the get default one. So how could you possibly avoid that? Well, time for Rust to enter the picture. So here's references.rust. And this is the same function. It looks a little different because it's Rust. This says map has type hash map from string to string. Key is a reference to a string. Default is a reference to a string. And it returns a reference to a string. And then you do map.getKey. If it's there, return that. Otherwise, return the default. That's what this code says. It's using
Is unwrap or that looks like a monadic function.
sort of. Yeah, I don't want to get too much into the Rust standard library, but that's basically what it's doing.
So Rust also has monads.
It doesn't have higher kinded types, so it has functions that look like monads look, but it has a different one for every type. If that
Okay.
makes sense. So yeah, we're looking.
Yeah, some and none. Those are like really simple monads. Those are
Yeah,
the only
so-
monads.
Yeah, so people who don't know Rust, some and none is like, instead of everything being able to be null, you like specifically say which types are able to be null, and the types that can be null are called options. So this is the documentation for option. So none is like null, and some is like not null. Yeah, so I don't want to get too far off topic. So this is get default, map key default. And let's see what rustc does. Is it going to let it compile? Hint, hint, no. All right, so it gives us a whole bunch of errors. What do these say? So first off, it says you didn't say how long the string is supposed to last. You said it's returning a reference, but we don't know how long. And it suggests, maybe it should live forever. Static is one of the... We were talking about static memory earlier. Static means it lives forever. So we're... this clearly doesn't work because these types don't live forever. The reference for map is a temporary reference, and so it's going to give us a second error. Well, we have 2 of these. Yeah. Oh, this code is hopelessly broken. Sorry. Let me fix this so it's not. The other thing Rust does different is that references are explicit, and you can't pass it in as if it's a value. Yeah, there we go. Okay. And then this I had to turn. Anyway, let me just comment this out for a second because it's not the bit I want to talk about. This says just crash when you get there because I don't know what to do. Okay, so actually that did more than I wanted. Let me go back to references too. So this is the fixed version. And this fixed version has a lot more stuff now. You can see what's this ret, what's this colon doing, why are these named references? What these are called are lifetimes. So this is the lifetime of the return value. This is the lifetime of the map right here. And this is the lifetime of the default value. And we didn't have to annotate the key because we don't use it very long. The second we return from this function, we ignore it. And then what this says is that the map outlives the return value, and the default outlives the return value. So if you return a value from this function, it has to live at least, it has to live no longer than the lifetime of the map and the lifetime of the key. And what that means is that our examples from before don't compile. And Rusty is catching our bugs here. It's saying borrowed value doesn't live long enough. You tried to assign to a local variable. This is line 20 here. You tried to return a reference to a local variable, and that doesn't work. It's going to be deallocated at the end of the scope here. Actually, it says that right here. It is returning value owned by the current function. So Rusty catches this cold. Like, this is something it does like all the time.
Wait, sorry to interject again. Just another question. So Rust basically allows you to do deallocation and reallocation almost in the type signature. So the type checker catches this, right?
Yes, exactly. In Rust, how long the value lives is part of the type signature. That's what this is here.
Okay. That's actually really dope.
Yeah, it's so cool. I love it.
So it's almost like if a ML language just decided to mix with C and take pretty much anything good from both of them.
This is exactly how I describe Rust. It's a weird mix of C++ and Haskell. Yeah.
And you even got pattern matching.
Yeah, you've got pattern matching. You got all these cool features, but like
Is
the killer.
pattern matching optimized in Rust?
Yeah, it's just like a branch. There's internally, so option, let me go back to it. Option looks like this in the standard library, none or some. And it'll actually do optimization. Say like t is a pointer or something. It'll optimize. Instead of taking, the size of t plus 1, it'll say, oh, we know that references are non-null in Rust, so we can use that 0 to represent null. So it's smart like that.
And I guess that would have to take somewhat of a performance hit at runtime compared to C++ with correct app.
Well, no more than checking for null would in C++. Right? So
Okay.
if you check for null in C++, that has about the same overhead as this match does.
I guess because, what do you call it? Deallocate, or not deallocate. What's it called? Deallocation, I guess. Or no, what, yeah. Screw it. I can't think of the word. Just continue.
Okay.
Sorry to bother.
Yeah, you're good. So Rust-C told us before that we're turning a reference to a local. So this function can't be written. It's if we have a map that we create in this function, we can't return a reference to it because it'll be gone at the end of the function. What we could do instead is like take the map in as a parameter. Hash map. I can't type. String. This is how you do generics, is the little angle brackets. And return from that instead. And unless I got my types wrong, this should compile. Yes. Oh wait, no, it's telling us now. Okay, if we're passing in a map, we need to actually pass in the map. So let's do that. I'm just passing in like an existing map I had here. Well, and
I
had a
know this
syntax
all
error.
looks really scary,
Okay, cool.
but living with a really useful type checker is literally a game changer. Like as I write more and more Haskell, you just learn to love it because you don't have to debug as much. You just get told by the compiler what's wrong with your program.
Right. Yeah, it's you pay like more upfront because you have to figure out, oh, what's this error, what's this like crazy thing the compiler's telling me. But on the upside, you don't have like memory bugs. Like they're just not a thing in Rust.
Like,
You mean one day I won't have to deal with a debugger?
Yeah.
there's a thing in OCaml where if you look at any library in OCaml, there are no tests. It's absolutely mind blowing that
Well,
literally almost every single library written in OCaml has no test folder.
I don't know if I recommend that, but you need less tests than you would in Python. I'd agree with that.
I just haven't found a like big OCaml library with a test.
Well, that's a little concerning, but but anyway, so it's been giving us a second error this whole time. What's the second error it's giving us? This is line 33. And so we've introduced a scope here. This is the same thing from before, but in miniature. Instead of having a function, we have like a little scope. Inner gets dropped at the end of the scope. And it's saying, okay, you can't set a reference to something outside of the scope that lives longer to something inside of the scope that lives for shorter. Yeah, and it actually says exactly that. Borrowed value doesn't live long enough. Questions on like borrow checking and lifetimes and what these words mean?
I have a question.
Yeah.
Can you modify a value's lifetime?
Like make it,
Can you define it?
well, the lifetime like depends how you use it. So say there's a function called drop, and drop just says like get rid of this, I reallocate the memory right now because I'm not going to use it again. If you then try and use it, so let's just print it out a second time. If you try and use it, the compiler, let me comment this out real quick. Yeah, all right. Yeah, okay. Yeah. Oh, well, that doesn't look right. Oh, S is a pointer, that's why. Yeah, it's making a copy. Let me just make this simple. Let S equals string. All right. So we're gonna print it out. We're gonna drop it, and we're gonna print it again. There we go. Okay. And it says, all right, you deallocate it here, so you can't use it again, right? But if we comment this drop out, if we say, okay, no, we do actually want to use it, then we can use it later. So the lifetime of the variable is dependent on how you use it.
Okay.
Does that sort of make sense?
Yeah. There's no way to like change the lifetime though. Say something you want it to live longer before it has died.
Yeah. So, you're saying like, say we want this like inner here to last for the whole function, sort of thing.
Yes.
Yeah. You move it outside of the scope.
Oh, okay.
And then what if you want like a dynamic lifetime?
Like you don't know when it's going to be deallocated.
Yeah.
Yeah. So
Like
you
if you
can.
have shared pointers.
Okay, shared pointer. So the way you do that in Rust is called RC, reference counted. Oh, hold on, I have too much stuff. Here we go, standard RC. And this stands for reference counter, so it's taking some struct, and it's keeping track of how many times you've used it. So let me find a good example.
So Rust must handle multi-threading pretty well.
Rust is excellent at multi-threading. I'm just going to write my own because I don't like the docs. rc.rust. Use...
Are those the docs that you wrote?
No, those are not my docs. Function main. All right. I can't type. All right, and I'm gonna say, so let's make a string rc new string from hi. All right, so this is our string here, and we'll print it out just to make sure that my life is sane. Yep.
Oh, so this actually acts a lot like monads, where even though you initiated it as a RC type, it could still just normally do the S type, like an IO monad.
I'm not quite sure what an IO monad is, but it
Neither
does
do I.
like okay, it does auto dereferencing is what it's called. So this is basically
Oh.
the same as this. It's saying, okay, we know RC is a pointer. We know you basically never want to print an RC, so let's dereference it for you. So let me just
I
show
don't
you.
like that. I would prefer if the type checker told me trying to print out a pointer.
Well, Rust doesn't think of them as pointers because it can't crash. There's no null pointers. So I don't know. If you really wanted to print it out as a pointer, you could do like as pointer const, but nobody does that. Oh yeah, and it says we don't know what a pointer should look like. It's just like random bytes. So I'm telling it just print it as a number. As raw, I think. Anyway, this is kind of not this thing I wanted to show. All right. Anyway, there's a function to print it as a pointer. I don't remember what it is, but
I see.
yeah. And then so what RC does is it takes your string that you already had, and what this RC clone is doing is it's not copying the whole string. It's just incrementing the reference counter by 1. And then we can print s2, and that's no problem. And that works. Right? And then if we drop s, if we drop the original string we made, we can still print s2. Because the RC, the reference counter, is what has the ownership, not the original string. And that
Any
works fine.
operating systems written in Rust then? There should be, because that totally takes
Yes.
away the problem mutex.
Well, it doesn't take it away completely, but it makes it a lot easier to work with. Redux, I think, is the one that you're most interested in. This is like an OS written in Rust. And they like wrote their own libc, and they're kind of crazy, but they do neat stuff. Other questions about Rust, about memory management, about C?
Sorry, this is probably a really like simple question, but right there, what you just did in that code, did you just declare a variable without giving a value? Essentially,
Yes, I declared a variable when I said I don't want to type out the type. The type here would be like RC. Oh, I can't. I had caps lock on. Sorry. The type if you wrote it out would be RC string. But I was like, I don't want to type out RC string. That's dumb. And the Rust compiler just figures it out for me.
all right. Sorry, I don't know if that's really simple question or not. I'm just a little early on in my stuff, so.
No, you're good. That's called type inference. It says, okay, we have an RC string on the right-hand side, so that must be what the left-hand side is.
If you're really interested on like type systems and all that, Haskell, ML are extremely strict, and it looks like Rust is a lot stricter than I thought. It's really cool how like, yep, that's it.
Yeah, this
Type
is like the normal algorithm for figuring out how do I make these two types, come together. It's called type unification. And I'll put this in chat for anyone who's interested.
So
Thank
it's
you,
similar
I
to using the
appreciate
word var.
Sorry, Colby?
Sorry.
It's similar to using the word var.
Yeah, let is like the word var in JavaScript. Yeah.
But JavaScript is completely duck type, right?
Yes. Yeah. JavaScript doesn't have type inference. It just doesn't have types. Yeah.
Well, I meant like I know in the newer versions of Java you can do that, and also in C# you can do that.
Yes. So this is actually the same as var in JavaScript and as auto in C++. Yeah, it does type inference.
Okay.
Type inference in C++ is kind of limited because they have like function overloading. So like say RC clone took, I don't know, both a reference to a string and like an owned string, then it wouldn't be able to figure out this type because it wouldn't know which function to call. In Rust, there is no overloading, so it always knows. So for example, say I do like struct s, and I try and implement the same function twice. I don't know, f taking, so this says I'm taking an instance of the struct s. Actually, let me just do constructors, that's easier. Function new, and it takes an int. This says it returns the struct. And it's just, there's only one thing it could be, so let me do this so it's a little clearer. Right, so this says create a new struct s that has like an inner type that's an integer. And this says, all right, create it with this integer. And like, say you want to overload it. And oh, now it takes unsigned integers, ooh. Rust will give you an error, it says this isn't valid code. Yeah, duplicate definition. So it doesn't have function overloading, which one is kind of annoying, but also you get really nice type inference. So, other questions?
Should we somewhat wrap up so that we can get to the elections?
Yeah, sounds
Or-
good. Thank you so much, everyone, for coming out. I had a ton of fun.
Yeah, this was really good. Thank you.
That was
I can
good.
see why you like Rust so much.
That's pretty dope.
Oh, where can I find the recorded thing since I missed probably the first 20 minutes?
Yeah, I'll be posting it after the talk. I'll put it on the website, I think.
Okay, cool. Thanks.
And probably in GroupMe as well, I'm guessing.
Yeah, I'll post it in different places.
Thank you.
Yeah, thank you guys.
Thank you. All right. So
Make sure to click stop recording, Josh.
Good point.